So what is electromagnetic spectrum? The electromagnetic spectrum is a range of all types of electromagnetic radiation. When we talk about electromagnetic radiation, it is the dynamic duo of electric and magnetic parts working together to travel through space. It is the reason we have light, heat, and more. So now let us look into the uses of electromagnetic waves in our daily lives. Radio basically captures radio waves that are transmitted by radio stations. Radio waves can also be emitted by gas and stars in space. This type of radiation is found in microwaves and helps in cooking. It is also used by astronomers to determine and understand the structure of nearby galaxies and stars. Infrared is invisible to the eye. It can be detected as a sensation of warmth on the skin. The visible light is a light that can be detected by our eyes. The sun is the main source of ultraviolet radiation. It causes skin tanning and burns. Hot materials that are in space also emit UV radiation. X-rays are a form of electromagnetic radiation similar to radio waves, microwaves, visible light, and gamma rays. X-ray photons are all highly energetic and have enough energy to break up molecules and hence damage the living cells. Gamma rays have the smallest wavelength and the most energy of any wave in the electromagnetic spectrum. They are produced by the hottest and most energetic objects in the universe.
All of these electromagnetic waves travels at the speed of light, which is 3 times 10 power of 8 meter per second. The speed of electromagnetic light is wavelength times the frequency. So as we move towards the right, towards the radio wave, the wavelength increases. As we move towards the left, the frequency increases. Now we need to learn the relationship between the wavelength, the frequency, and the energy. So as the wavelength increases, the frequency decreases, and so for the energy it will decrease as well. But if the wavelength decreases, the frequency increases as well as the energy. So by now we know that the speed of light is equal to the wavelength times the frequency. And the speed of light travels in space at 3 times 10 to the power of 8 meter per second. And now the energy of a photon is equal to Planck's constant times the frequency. So Planck's constant is 6.626 times 10 the power of negative 34 joules times second. Now let's work on some problems. Given you have a 700 nanometer and you are asked to find the frequency. For you to easily remember the formula, you may refer to this, which is the constant over the frequency times the wavelength. The wavelength and the frequency can be interchanged, but not for the constant. So you are asked to find the frequency. So the formula is the constant over the wavelength. And you next is you just have to substitute. So remember that the constant is 3 times 10 to the power of 8 meter per second. So we are going to substitute the values. So for the constant, you just plug in 3 times 10 to the power of 8 meter per second. As for the wavelength, you cannot just plug in the 700 nanometers because you will have a mismatch of the units. So you can convert the 700 nanometers into meters, which is 1 nanometer is equal to 1 times 10 to the power of negative 9 meters. So if we plug in the 700, that would be 700 times 10 to the power of negative 9 meters. And you can just compute it. So the frequency is equal to 4.286 times 10 to the power of 14 hertz. The unit for the frequency is hertz, and for the wavelength, it's in meters. So after getting the frequency, we can now get the energy, which is the energy is equal to the Planck's constant times the frequency. So that would be written as 6.626 times 10 to negative 34 joules times second, multiplied by our frequency, which is 4.286 times 10 to the power of 14 hertz. So hertz can be written as 1 over s, because remember earlier we can cancel this meter, and what's left is the seconds. So now if we can see, as we can see, we can cancel the second, and we then multiply, which gives us 2.84 times 10 to negative 19. Because we cancel the second, we are then left with the joules. Now, what if we are asked to find the wavelength? If we are given a value of frequency of 1.692 times 10 to the power of 15 hertz, we are going to use the triangle, which is C times frequency times the wavelength. So we are asked to find the wavelength, so we can use this too. So the wavelength is equal to the constant over the frequency. So if we are going to substitute this will become 3 times 10 to the power of 8 meter per second. And for the frequency is 1.692 times 10 to the power of 15 hertz. So hertz can be written as 1 over second. So as you can see, both the denominator and the numerator has seconds, so we can cancel this one, and then we proceed to computing. So if we divide the given constant and the frequency, we will have 1.773 times 10 to negative 7 meter. So this is now our wavelength, and that is how you calculate the wavelength. Now, if you want to convert the value of wavelength in nanometers, you can write it as 1.773 times 10 to the power of negative 7 meter over 1 times 1 nanometer over the value of 1 nanometer, which is 1 times 10 to the power of negative 9 meter. We can just then cancel the meters. So we can take this value to the numerator so that the negative 9 becomes positive 9. So we can then multiply this, written as times 10 to the power of 9. So in the rules of multiplying with exponents is you can add the exponents. So if we are going to multiply this, it will become 10 to the power of positive 2. So we all know that 10 to 10 squared is simply 100. So we can write this as 177.3.
Rydberg equation, it was later found that N2 and N1 were related to the principal quantum number or energy quantum number. This formula works very well for the transition between energy levels of hydrogen atom with only one electron. For example, calculating the Rydberg equation, calculate the wavelength corresponding to the transition from Lenmar series to the third energy level. The wave number is equal to the Liv x content, and then of course in the brackets we have 1 over the initial of 1 squared minus 1 over the initial of 2 squared brackets squared, so light big is a constant. We know it's always going to be a given to us. It is 10, 973, and 731.6 meter negative. So we have wave number on the left hand side, and then in the brackets line, Man City is associated with the first energy level. Yeah.
So we need to picture in mind that this is an emission. So having an electron moving from the first energy level all the way up to the fed energy level, so we expect that there is a gain of energy there. So here we have our energy, our wave number. Our wave number is 1 over wavelength, so it is equal to gawing a calculator. This 1 over 1 squared is just 1 minus 1 over 9, which is obviously going to be 8 over 9 multiplied by 10 900 973.1.6. So the answer I'm getting is the answer is 9.754 times 10 to the power of 6 minus negative. We just we just have to divide it. If we cross multiply, you end up dividing one by the answer. Then we get So our wavelength our wavelength is our wavelength is 1.0225 by 10 the power minus 7 in meters. So that is how you apply the Rydberg equation to performing calculations.
You probably know that matter is made up of tiny particles called atom. But how does really atom works? And what is inside an atom? In 1913, a Danish physicist named Niels Bohr was curious about how really atom works. Through his curiosity, he made his own theory known today as Bohr's theory. But before we discuss about Bohr's theory of atom, let us explore first his life. Niels Bohr was born on October 7, 1885 in Copenhagen, Denmark, and died on November 18, 1962 in the same location. He completed PhD in physics in 1911 from University of Copenhagen. He worked under Ernest Rutherford and later on developed his own theory of atom from previous studies, and won Nobel Prize in Physics in 1922. Niels Bohr and his theory of atom are truly remarkable. And now, we will go back to his theory to understand it better. In his theory, it first proposed that the electrons revolve around the nucleus with a definite energy levels called orbits or shell, where shells are represented by the letter K, L, M, N, and so on. The maximum amount of electron that can accommodate in an orbit is 2n raised to the power of 2, where n is a number of orbit. Now K shell would have 2 electrons, L shell would have 8 electrons, M shell would have 18 electrons, and N shell would have 32 electrons, and so on. Bohr also proposed that the orbit closer to the nucleus has minimum amount of energy if we compare it to the outermost shell that has the maximum amount of energy. If you look at the image, when electrons are in excited state, they jump between orbitals. The electron takes on the energy of the orbital that it is in. If an electron jumps from a higher energy orbitals to a lower energy orbital, that energy is released in a form of photon. Note that electrons do not radiate by itself, but when an atom absorbs energy, electrons get excited and jump into orbitals. And that's the end of our lesson. I hope you learned something, and thank you for watching.